Alright everyone, this week we're going to still be looking at limits questions, and we're going to be looking at three in particular: limits of trig functions, limits of piecewise functions, and limits using conjugates. Now the first two, limits of trig and limits of piecewise, still technically fall into find limits by substitution and find one-sided limits. It's just this time we're going to be looking at those as function values, not necessarily graphs. And then our last one, limits using conjugates, that's still going to be kind of related to the limits by factoring question that you saw last week. So you're going to see 0 over 0 show up, and there's going to be work to do to find the answer. So let's just go through the three assignments, but again, at the end of the day, we're working on these two standards right here, which are finding limits by substitution and finding one-sided limits. So let's get started with limits of trig functions. Now, things to keep in mind is you're going to have to know your unit circle pretty well to navigate through these. But this says find the limit as x approaches pi over 6 for sine of x, and that just means you need to know the y value, sine is the y value, at the radian pi over 6. So hopefully you have your unit circle. I guess I'll pull one up. Should have had that beforehand, but oh well. Okay, so at pi over 6 you can see the y value is 1/2, but hopefully you had that memorized and you were good to go. Okay, up next, find the limit for secant as we approach pi over 3. Now, secant is related to cosine. It's what you get when you flip cosine's value. So we'll find cosine at pi over 3. So pi over 3, cosine is x, that's 1/2. When you flip 1/2, that's just 2. All right, because remember, secant is cosine flipped. So I'll maybe pull this up and look at one more or two more, so I technically did all 4 in the assignment. Okay, secant of pi over 2. Now that's flipping the x value at pi over 2. So at pi over 2, the x value is 0. Now I'm going to use the page over here. Remember that 0 is technically 0 over 1. So when you flip that to go to secant, you'll end up with 1 over 0. So secant of pi over 2 is 1 over 0, but anything over 0 is an asymptote or a undefined limit. Last question here. Cosecant as we approach 0, this looks like this might be the same type of problem, because this time cosecant relates to sine. So sine of 0 would be 0. Right, so again, sine of 0 is 0, which is technically 0 over 1, but we want cosecant of 0, so we flip sine's value, and again, we have that asymptote. When 0 is in the denominator but something else is in the numerator, that's going to be an asymptote, which means your limit is not going to exist. Maybe one more, tangent of pi. So this is where it's super important to remember that tangent is sine over cosine. So this is really saying what's sine of pi divided by cosine of pi. And the y value at pi is 0. The x value at pi is -1. Now this time, this is just 0. All right, so know the difference between being undefined and just being 0. All right, so that's the first one. And really the idea is, if you especially look at what we did here, it's not that we were really thinking about limits, we were just directly substituting. What do I get when I plug in pi? What do I get when I plug in pi? That's what direct substitution means. All right, up next we'll look at piecewise functions. This will be where things get a little bit more interesting, because this question right here says find the limit as x approaches -3. Now if you notice, we have this piecewise function here, and the problem with this piecewise function is it's split at -3. So here's what I'm going to do for this question just to build up the idea of what's going on here. I'm going to go to Desmos. I should do this in a separate tab so I still have my unit circle. It's been a while since I've used Desmos, but I think I'll be able to write it like this. Equal to x less than or equal to -3. Okay, so you can see we definitely have a piece now. That's why these are called piecewise graphs. And then we're also graphing x squared minus 5, but we're only graphing x squared minus 5 if x is greater than -3. Okay, so you know, this kind of gives it away. You can definitely see what the limit's going to be now. Sorry, I should zoom in like this so that it stays nice and crisp. The idea is this limit at -3 is totally split. Now, we're going to figure out how to do this without looking at the graph, but I just wanted to show you the idea of a piecewise graph one more time. So, I mean, if we zoom out, you can see the red graph what was written up here. This function, you might not know how it's graphed, but hopefully you do kind of see where this is coming from, being it's a square root and everything. You can see it only exists for the x values -7 to -3, and whatever your y values are, they're just kind of showing up there. And then this blue graph is x squared minus 5. It's a quadratic moved down 5, but notice it stops at -3 because we're only allowed to be greater than -3. So if you actually, again, technology won't show you holes unless you're very specific with them. You can see there is an open circle on the blue. Just kind of reviewing how piecewise functions work. Again, hopefully that kind of makes sense. But the idea is, hopefully you would say, if this were a graph on Khan Academy, what's the limit as you approach -3? Well, the limit clearly does not exist because from the left in the red, you're approaching 2. From the right in the blue, the right side of -3, you're approaching 4. And since 2 and 4 don't agree, you would say the limit does not exist. But how on earth do you figure this out without looking at the graph? Well, here's what you do. Just plug in -3 for both. So again, keep in mind the red graph goes to 2, the blue graph goes to 4. And the idea is we could just try direct substitution. So let's just plug in -3 for what's going on technically the left. That's the important thing, that you can read this and say, okay, this function exists on the left. Its x is less than the part that I care about. So this is the left-sided part of the graph. That's what you need to know without looking at the graph. Okay, so for that part, again, if I just plug in -3, I would have the root of 7 plus -3, but that would just be the root of 4, which is 2. And the right-sided limit would be when you plug in -3. Now when you plug in -3 for the right side, again, hopefully you can see that it's the right side of -3 because you're larger than -3, so think about the number line there. But when we square that, that's +9 minus 5 is 4. So again, what I said before about the graph, the left-hand side is going to 2, the right-hand side is going to 4. You see that clearly from the algebra. And since the left and the right don't agree, the limit doesn't exist. So we'll do that 3 more times, only now we're going to go away from looking at the graph. So this time, here's where things get interesting. They don't even ask you for the general limit. They get particular with you. They say they only want the limit as you approach pi from the right. Now you need to look at this and figure out which one of these is saying you are right or greater than pi, and it's this one right here. So since this is the one we care about, since we're trying to approach it from the right, and this function is on the right-hand side of pi, it's greater than pi where it's defined, we just plug pi into sine. So what is sine of pi? Again, unit circle. What's the y value at pi? The y value at pi is 0. So the one-sided limit definitely exists. You just find which side it corresponds to. So again, since this is saying x is greater than or equal to pi, it's not the equal to that matters, it's strictly the greater than that matters, because from the right means you're going to be a larger value than your value of interest. And we'll do this a few more times. Again, the limit as we approach 4. This time, again, 4 is split on both sides. This would technically be the left-handed limit because it's all the x values less than 4. So we're approaching from the left, and these are the values to the right. So let's see here, the left-handed limit this time, when I plug in, if I plug in 2 to the 4 for the left-sided limit, I'm going to get 2 to the 4th power is really just 2 times 2 times 2 times 2. So that's 4 times 4. So this is 16, right? And on the bottom, 8 times the root of 4. So this is the right-sided limit. We're just plugging in for the function that's defined on the right side of 4. And that's 8 times really 2, so we also get 16. Now this time the left-handed limit and the right-handed limit agree. So the general limit is what the left-hand and right-hand limit both say they are. Right? When they're the same, that's what the general limit is. Last but not least, okay, this is my, I guess, quote-unquote favorite question, or it's the one that's the most interesting, because this is where you have to pay attention. This time it's the limit as we approach 1, and notice here, 1 is not what I call the break point of this graph. The break point, where it splits into 2 different pieces, happens at 0. Now, since we care about the limit of 1, you just need to read these conditions and figure out, well, which one contains the value +1? And this is the one that reads true. If you plug +1 into this, is 1 greater than 0? Yes. But is 1 less than 0? No. So since this is the one that reads true, you're only going to plug 1 in here. This is a special question. You're going to want a calculator. ln of 1, you probably don't know that, but it turns out the answer to that is 0. So the idea is, in all of our previous questions, where we were finding the limit was at the break point of the graph. So we had to kind of consider where both sides were. This time, where we evaluated the limit was only contained in one part of the graph. So we only plug it into the one function and get our answer and move on. All right, hopefully that helps. If you have any questions,